going to work through the problems from the Chapter 8 slides, and this chapter is focusing on hydrocarbons. So hydrocarbons are molecules that have only hydrogen and carbon atoms in them. We're going to look at three different types. The first type is going to be alkanes, and the difference in each of these is always going to be this middle letter. So alkanes are hydrocarbons that have only carbon-carbon single bonds. So all of your carbon bonds in your structure are going to be just single bonds. If this is the case, the relationship between carbon atom count and hydrogen atom count is always going to be the same. So for the general formula for alkanes is CnH2n plus 2. What this means is if you know the number of carbons, which would be n, you can take that times 2 plus 2 to get the number of hydrogens. You can also figure out how many carbons if you know hydrogens, set that number equal to 2n plus 2 and solve for n to get carbon. So here's a couple examples. We know we have 6 carbon atoms for the first one. So that means we're going to be doing 2 times 6 plus 2 to get the number of hydrogens, which would be 14. The second example, we know hydrogen is 8. So that means the 2n plus 2 has to equal 8. If we solve for n, we find out we have 3 carbons. Let's go ahead and pause your video and see if you can solve the last 2 examples. All right, your last 2, you should come up with 2 times 9 plus 2 is equal to 20. Last one, 2n plus 2 equal to 32. N is going to be 15. Next, we're going to draw some alkanes. So because alkanes are all carbon-carbon single bonds, you're just going to connect all of your carbons with single bonds first. Then you're going to go back and fill in to make sure carbon always has 4 bonds. Whichever bonds are missing, you're going to put in hydrogens. So first example, C6H14. We'll draw out 6 carbons with single bonds in between them. So that's 5, 6. The carbons on the end have 1 bond each, so that means they're missing 3. So we'll stick 3 hydrogens on each of those. Then if we look at all the carbons in the middle, they've got 2 bonds. So that means they're all missing 2 bonds, or 2 hydrogens. We'll draw those in. So there is your C6H14. So notice we're not counting electrons like we did drawing Lewis structures before. We're always going to make sure carbon has 4 bonds and it'll fill in the right number of hydrogens. For the second example, we've got 4 carbons, all with single bonds. Again, each on the end need 3 more. And then the 2 in the middle both need 2 more. And there are your 10 hydrogens. So pause your video and see if you can draw the alkane with 5 carbons. Notice here we're not even giving you the number of hydrogens. You don't need it, just make sure carbon has 4 bonds. The other thing you can do is remember you have your 2n plus 2 rule, so that means your problem or your structure should have 12 hydrogens. So go ahead and pause and draw that structure. All right, so C5H12, you should have your 5 carbons. The carbons on the ends both get 3 hydrogens, and then all of them in the middle will get 2. And that took 12 hydrogens. So that's how you draw alkanes. The next hydrocarbon are the alkenes. So notice the A changed to an E. Alkenes are hydrocarbons that have at least 1 carbon-carbon double bond. So somewhere in our structure we have a double bond. For this to be the case, if we know the number of carbons, hydrogens are going to be just twice as many. So we're getting rid of the plus 2. The reason is when you add the double bond in between 2 carbons, you have to lose 2 hydrogens to do that. So you can't give carbon more than 4 bonds. So same idea as the first slide. This time though, we're just going to multiply by 2 or divide by 2. So 6 times 2 gives us 12 hydrogens. 2n equal to 8 means there must be only 4 carbons. Go ahead and pause and finish the last 2. All right, if we have 9 carbons, we're going to do 9 times 2 is 18 hydrogens. Sorry, my cat literally just jumped across my lap. All right, and then the last one, 2n is equal to 32, which means we're going to have 16 carbons. For drawing alkenes, again, we're going to connect all of the atoms with, or all the carbon atoms with single bonds. Then you're going to add a double bond somewhere. Unless there's something in the name that you're given or in the directions, the double bond can go anywhere. Then you'll go in again and fill in with hydrogens to make sure your carbon has 4 bonds. So first example, we've got 6 carbons again. I'm going to stick the double bond in the middle, but it could be between any of the carbons. It doesn't matter. So this first carbon on the end needs 3. This next one needs 2. The next carbon already has 3 bonds, so it only needs 1 hydrogen. Same for the next one. Then we're back to a carbon with 2 bonds, so it needs 2 hydrogens. And the one on the end needs 3. So that's one example. You could have that double bond anywhere along the chain. C4H8. This time I'm going to put it on the end, just to show you an example of that. So now this carbon on the left currently has 2 bonds, so it's missing 2 hydrogens. Next one has 3, so it's missing 1 hydrogen. Next one has 2 single bonds, 2 hydrogens, and then the one on the end needs 3. Go ahead and pause the video and see if you can draw the alkene with 5 carbons. So if it has 5 carbons, that means your structure should have 10 hydrogens. So if we stick our 5 carbons together, you could have put your double bond anywhere. I'm going to put it over here. 3 hydrogens on this end, 2 here. Next carbon already has 3 bonds, so it's 1 hydrogen. Same with the next one. And then the one on the other end also needs 3. So there's drawing your alkene structures. One other thing we have that's special about alkenes are the cis and trans. So double bonds do not rotate. That means they're kind of locked in that position. And when that's the case, you can have several different orientations. So if we look at our double bond, the best way to do this is draw a line through your double bond. And then what you're going to want to do is look to see where your carbon groups are. So here are the 2 carbon groups coming off of that carbon double bond. And what we get are the 2 carbons are on the same side, so that is cis. If we look at the next example, we've got carbons on the opposite side of the double bond. That is trans. The last example, we actually have 3 carbons coming off of the double bond, so this is neither. You have to have 1 carbon coming off of each end to have cis or trans. If you've got 3 carbons total, or if you only have 2 coming off of the same carbon, that would be also neither. We're also talking about physical properties for the hydrocarbons. Earlier in the notes, you found that alkanes have a boiling point depending on how the length of the chain goes, right? Alkenes are also going to be following the same pattern, but what we're now going to look at is the comparison between alkenes and alkanes. So alkenes are going to have a slightly lower boiling point than the alkane, and the reason for that is because it's smaller. So alkenes have 2 fewer hydrogens. And if you remember back in chapter 7 when we talked about ranking boiling points, if it came down to London forces, it was based on size. So here we've got weaker London forces. Means we're going to have a lower boiling point for the alkenes. Another comparison that we can do is the trans versus cis. Trans is going to have a higher boiling point than cis simply because it stacks better. So the trans structures are pretty flat Even though they've got this zigzag pattern to them, overall it's a very flat molecule. So you can stack them very well, which means they're going to have very good interaction with each other, which is going to lead to a higher boiling point. For the cis molecule, you have kind of this kinked structure to it, and these won't stack very well. So that means the boiling point will be lower. So if we take all of this into consideration, right now we know that alkanes have a higher boiling point than alkenes. And if we're comparing alkenes, trans have a higher boiling point than cis. So this first example is a cis alkene. Here we have an alkane, and then the other one is a trans alkene. So the alkane is going to be the highest, and the cis alkene is going to be the lowest. The other piece with the double bonds is some discussion on saturated versus unsaturated fats and oils. So saturated fats contain all carbon-carbon single bonds, so we can think of these as alkanes. Unsaturated have double bonds in them, so these are alkenes. Just like we ranked boiling points, we can think about melting points as well. So the alkane is going to have a higher melting point than the alkene. So that means the alkane, or the saturated fats, are more likely to be a solid at room temperature. Higher melting point, you have to heat to get it to melt into a liquid, versus a low melting point where it might already be a liquid. Here's a couple structure examples. So here everything is single bonds. It's saturated, which we said that is an alkane. Here we have a trans double bond, so trans alkene. Here we have a cis double bond. So if we go back to the rankings that we're doing with boiling points earlier, same with melting points. Alkane is going to have the highest melting point, and the cis alkene will have the lowest melting point. In the next video, we will talk about alkynes and the rest of the problems. So go ahead and find part 2 of chapter 8 to see the rest of the answers.